안녕하세요. 오늘 여기에 초대해 주셔서 감사합니다. I'm going to talk about 4d-2d correspondence, which is based on several papers written together with great Caltech postdocs, Abhijit and Pavel. One paper appeared back in the winter, and that appeared just last week. So by now, everybody knows correspondence between two-dimensional manifolds, namely Riemann surfaces, and four-dimensional n=2 gauge theories, labeled by those Riemann surfaces. And the rules for building 4D gauge theories can be expressed in terms of pairs of Pen's decomposition of the Riemann surface. Namely, you chop the Riemann surface into basic building blocks and follow analogous rules for constructing supersymmetric 4D gauge theories. 2 years later, namely around Strings 2011, another class of theories in 3 dimensions with n=2 supersymmetry was introduced, where analogous rules of building 3 manifolds were transformed into rules of building 3-dimensional gauge theories with n=2 supersymmetry. The building blocks and resulting theories here are pretty much simple, so they're always expressed in terms of a billion degrees of freedom and charged chiral multiplets. But what makes the story interesting is not so much the final result or its ingredients, but rather the moves or transformations on a 3-manifold that translate into dualities and transformations of the 3-dimensional supersymmetric gauge theory. Well, it's been 2 years since 2011, and it's also Strings, so it's about the time to move on next step. And in this talk, I'll introduce theories of class H, which are 2-dimensional theories of heterotic type. By this I mean with 0, 2 supersymmetry in 2 dimensions, labeled by 4-manifold. And again, just in the predecessors, the basic building blocks and moves and transformations of the 4-manifold will translate into operations on the corresponding field theories. I cannot tell you why these theories are called of class S. For this, you better ask Greg, Andy, or Davide. Well, even though this is my cup of tea, I cannot tell you why these theories are called of class R, except that R is just next to the S in the alphabet. But I can tell you why we call these theories of class H, breaking the pattern a little bit. Well, 4-manifolds in general are labeled by their Betti numbers. That's the crudest topological description of the 4-manifold. And in my talk, I'll limit myself to simply connected 4-manifolds. In those cases, they're just labeled by 2 integers, which could be expressed as early characteristic and the signature. And this plane, 2-dimensional plane, basically summarizes different basic types of 4-manifolds, where one acts as early characteristic and the other is signature, or some combinations thereof. This is very poor approximation to topology, because unlike Riemann surfaces, in which specifying the genus or early characteristic was enough to specify topology, in the case of 4-manifolds, Betti numbers or these 2 integers is not enough by far. However, at the level of numerology, these 2 integers, or the characteristic and the signature, do translate to the basic information about the 2-dimensional 0-2 theory, namely the left moving central charge and the right moving central charge. What this plot shows is the mathematician's view of these Betti numbers, or basic topological characteristics, which say that 4-manifolds of smooth type cannot exist in certain regions bounded by various lines in this plot. So it is natural to think that they will translate to some sort of unitarity bounds, or bounds on central charges of 2-dimensional theories, according to this correspondence I'm going to explain to you. The real story is a little bit more interesting, a little bit more complicated, but I want to point out that on this plot there are several points which you can recognize and which were in fact mentioned in previous talks. This point here corresponds to K3 surface, manifold of Kummer surface, and the corresponding theory is going to be a roll sheet CFT of a heterotic string. So this entity in the correspondence we already know. And this point here corresponds to what's sometimes called half K3 or Delpezzo 9, and that's used in the construction of so-called E strings. And then the goal of this talk is to extend these several examples, plus a couple of others, K3s with frozen singularities, CHL strings, and so on, to much, much larger territory, and in fact construct such 2-dimensional 0-2 theories labeled by much more general 4-manifolds. Well, Few words of motivation why 0-2 two-dimensional theories are interesting. Besides their application for heterotic model building, they're just interesting field theories. It is known that two-dimensional theories with 2,2 supersymmetry are somewhat similar to four-dimensional n=2 physics. There are lots of exact protected quantities, and many phenomena are very similar. Likewise, theories with 0-2 supersymmetry in 2 dimensions are somewhat similar to n=1 four-dimensional models. They may exhibit supersymmetry breaking, a lot of interesting gauge dynamics, and interesting question to ask here, do we know any kind of dualities just from the gauge dynamics point of view, which are perhaps analogous to Seiberg dualities in four-dimensional n=1 theories? So while thinking about this question, I came to realization that we actually don't. And this is probably a great venue to ask anybody in the audience if you know any interesting non-trivial statement about non-abelian gauge dynamics in two-dimensional theories with 0-2 supersymmetry, please tell me. Recently, there has been some good progress in abelian versions of such theories by this group of people who realized that there are actually new interesting terms analogous to the twisted superpotential in 0-2 Walsh-Sheet theories, and this will play an interesting role in our story here. So beside these motivations and several others which I listed on the previous slide, I have a couple of motivations which are dear to my own heart. One has to do with surface operators. If you look at the surface operator in four-dimensional field theory with n=1 supersymmetry, it will carry 0,2 supersymmetry in 2 dimensions. And moreover, if you take such a surface operator and consider its normal bundle to be a cigar, or equivalently compactify on circle, which is an orbit of rotation symmetry in the normal direction, you'll find a three-dimensional physics. That's a usual circle compactification, but it will be half space with a boundary because the cigar has the tip, and the surface operator now will translate to 0,2 boundary condition in three-dimensional n=2 gauge theory. And this is actually something that we'll encounter in the rest of this talk. Another motivation from completely different direction, but also very dear to my heart, has to do with physics of knot homologies, which can be realized in terms of BPS state counting. It is well known by now that BPS states, namely closed BPS states, form an algebra, and recently it has been much more precise through the work of Kontsevich and Soibelman, but it goes back to work of Harvey and Moore. Less known is that open BPS states form a module or representation for this algebra. This fact recently led to very rich algebraic structures in knot homologies, which in turn seem to have interpretation through four-dimensional cobordisms, which interpolate between three manifolds where these knots leave. And that, again, motivates studying 5 branes on 4 manifolds. So now I'll come back to my original subject and try to study the correspondence between 4 manifolds and two-dimensional heterotic-like theories. The basic feature, well, given such theories labeled by 4 manifolds, one can study lots of observables, like sphere partition functions, torus partition functions, and so on. I'll focus on the index, which is the torus partition function. Indeed, through the radial quantization, any d-dimensional field theory index can be expressed as a partition function on a circle times a sphere of 1 dimension less, and because we're here just in 2 dimensions, there is not much left, it's just circle cross a circle or a torus, if you wish. So therefore, you obtain a relation between partition function on a torus, or so-called flavored elliptic genus of the 0-2 theory, and if you use the standard reduction of 6-dimensional 5-brane theory in a different order, here reduction of this theory on a torus will give you n=4 super Yang-Mills, and in fact the twist I'm using here, secret twist along the 4 manifold, is precisely the so-called Waffe-Witten twist, which leads to partition function that counts Euler characteristics of moduli spaces of instantons. So somewhat new feature of this phenomenon is that there are additional fugacities or variables which count Chern classes of gauge bundles on this side, or parameters or fugacities which count flavor charges or global symmetry charges on this side. So this is not the usual elliptic genus. In fact, we set Jacobi variable y in the previous talk to be 0, so we don't care about left-moving U1R charge, but we do care about global symmetries. And this is the standard superconformal index viewpoint on the elliptic genus. If our theory, two-dimensional theory, contains gauge groups and matter fields, it's usually expressed as integral over the Cartan of the gauge group and various ingredients for the matter fields. In this talk, I'll give you two results about Vafa-Witten partition function on general 4-manifold. For more general results, I refer you to the paper. So this will be just a tiny snapshot of a much bigger correspondence. And one result is that surprising fact, which hasn't been noticed before, that if you're trying to glue a 4-manifold from basic pieces, then you quickly come to a realization that the measure for the integrand in this gluing of Vafa-Witten partition function is precisely the superconformal index of 0,2 vector multiplet. This fact is based on certain orthogonality property of Kac-Moody characters, which apparently was missed in the mathematical literature, even though this is a purely math question. So now let us try to rediscover or recover the general features of this correspondence between 2D theories and 4-manifolds. Suppose your 4-manifold is stretched along a long neck, indicated here. So you have a 3-manifold cross R, which is a very long interval. Then 5-brane theory on 3-manifold gives rise to 3-dimensional n equals 2 field theory. I'll call it T of M, now in this case, T of a 3-manifold. And if this was the whole story, it would be 3-dimensional theory on a 3-space, and this would be infinite range. However, because this cylinder, 3-manifold cross R, is kept off on both sides, it gives rise to 0,2 or B-type boundary conditions, where each boundary condition carries some modes associated to theory T of 4-manifold for this part and T of a 4-manifold for this part. So there are some degrees of freedom captured by 0,2 two-dimensional dynamics which are trapped on the boundaries of this space. And in this way, you can represent the whole thing as a result of sandwiching 3-dimensional n equals 2 theory, which is associated to the 3-manifold in a cross-section, now sandwiched by boundary conditions, B-type boundary conditions, you could call them branes, I guess, which are associated to non-compact 4-manifolds which have a 3-manifold on the boundary, and they're glued together along the same 3-manifold. So that's a very useful perspective. We are going to use it a little later. And here I will point another interesting feature of this correspondence, which is new compared to theories of class S or class R. You don't hit it until you go all the way to 2 dimensions, compactifying on a 4-manifold. Namely, 0,2 theories in 2 dimensions are famous for their anomalies, and this story is full of anomalies. First of all, in 3 dimensions, n equals 2 theories that we're going to encounter have lots of Chern-Simons terms. And in presence of boundaries, there could be gauge non-invariance due to Chern-Simons couplings. Correspondingly, these 2-dimensional 0,2 theories labeled by 4-manifolds are also anomalous in general. And even though in construction of heterotic string theories we usually discard anomalous theories, here they have proper place, and as long as their anomaly cancels the anomaly inflow from the bulk. And in fact, in many of the models that we have, this is exactly what's happening, realizing a phenomenon pioneered by Cullen Harvey in the paper from almost 30 years ago. In fact, some of their simple models where you have chiral fermions on the boundary canceling the anomaly of Chern-Simons terms is exactly what's going on here. Moreover, in the literature on 0,2 heterotic-like theories, it has been proposed by various groups that you can balance off anomaly due to chiral fermions by WZW terms. And all those models have very nice realization here, where instead of WZW terms, you have Chern-Simons action in one extra dimension compared to the worldsheet of heterotic theory. If you view this problem from the vantage point of the 4-manifold, even more interesting things happen. It's known that in the presence of 4-manifold with non-trivial topology, the D4 brane partition function, or its gauge field, may actually transform not like a usual gauge field, but rather behave as a spin-C structure, which was emphasized by Fried and Witten. This is called Fried-Witten anomaly. And here, since we'll talk about glue in four manifolds from basic pieces, something interesting happens, which has not been discussed in the literature until so far. Namely, what may happen is that you have one building block, say half of the manifold, which is spin, so there is no Fried-Witten anomaly here. Another half, which is also spin, there is no Fried-Witten anomaly here, but when you glue the pieces together, you suddenly find that your result is non-spin. How could this possibly happen? At first, when you encounter this, it sounds like a contradiction because you would think that existence of a spin structure is just described by characteristic classes, but the story is a little bit more subtle, and solution to this is very simple, instructive, and I invite those of you who like topology and anomalies as much as I do to think about this during the rest of my talk, and I'll be glad to reveal the answer in the very end. So this is a very nice phenomenon. Now, in the previous slide, we discussed stretching four manifold along a neck where you saw a three manifold as a cross-section. You can consider opposite situation where you have two three manifolds, this one and this one on the boundary, and a four manifold which interpolates them between them. That's a cobordism four manifold between two M3s. In fact, here I described how they're embedded in ambient space, and embedding of a four manifold is supposed to be inside G2, which gives rise to the Waffe-Witten twist. Now, by now you know the dictionary, and with our little experience from the previous slides, you can actually try to guess what's supposed to happen. The five-brane theory on a three manifold, either on this side or this side, gives you three-dimensional n equals 2 theory. Well, they could be different in principle if these two three manifolds are different. Now, four manifold gives rise to a two-dimensional theory, which is supposed to be coupled to both of them, and this is nothing but a half BPS interface, which carries two-dimensional 0-2 gauge dynamics trapped on the interface between these two theories and makes the coupling. So these are some of the general features, and in the next part, I'll try to describe a little bit of concrete things. So this will be, these general properties of what corresponds to what will be a useful guide for some of the explicit results I want to mention. For this, we have to go a little bit further, and I have to tell you how four manifolds are built, or if we're talking about two-dimensional theories labeled by four manifolds, natural question we should answer is, what are the four manifolds labeled by? Analogous to pair of pence decomposition, which is not going to work here, or triangulations, which were used in 3 dimensions, but they have their own limitations. Decomposition of 4 manifolds in the math literature goes usually in a handle decomposition, where you start with a 4-dimensional ball called a 0 handle, then attach to it 1 handle, 2 handle, 3 handle, and so on. All of these are topologically trivial. They are homoeomorphic to the balls of suitable dimension, in this case dimension 4, but they attach differently to the boundary of this 4-dimensional ball called 0 handle, which is depicted as a 3-dimensional sphere, and it is in this 3-dimensional sphere that we usually draw how all these other handles get attached. So this is a picture of, so this is already supposed to be 3-dimensional S3, which is boundary of a 0 handle, and it shows attaching regions of 2 handles, 0 handles, and so on, and the corresponding 4 manifolds that you get as a result of it. So 2 handle is a circle which could be possibly knotted, or if you have several of them linked with other components, labeled by an integer which is called the framing coefficient. And what's shown here is a touching region of a 1 handle, and as you can see, the corresponding manifold immediately becomes non-simply connected. So that's actually the general feature of 1 handles. So if you use them in the construction, you're typically going to end up with non-simply connected 4 manifolds. So we're going to use only 2 handles, which are essentially knots and labels. So we restrict to the class of 4 manifolds which are labeled by knot components and integer labels which are attached to them. So this is an example of a non-trivial 4 manifold corresponding to this pretzel knot with some coefficient which doesn't even have to be positive. So In this diagram, it's actually very easy to read off the intersection form of the 4 manifold that you build. That's a basic information about the 4 manifold. The number of components, link components, or these knots, is exactly the rank of second cohomology, so that's the second Betti number. The linking number between components, as well as these framing coefficients, give a quadratic bilinear form, which is the intersection pairing of the 4 manifold, of the second cohomology. In some cases, but not all, you can express this data in terms of a graph, which is very similar to the quiver diagram that we usually use to describe field theories. And this will be a nice class of examples. In the previous slide here, I used some unknots in this case. For example, you can get S2 cross S2, CP2, and so on. This is much more complicated knot. But the easiest manifolds, as you can see, could be built just with unknots linked in a certain pattern. So let's restrict to those. And this gives rise to what's called plumbing graph. So this is a Kirby diagram. It represents attaching reachings of two handles, these unknots, chain of unknots with various integer coefficients. And you can express this same information, as long as your knots are just unknots, as associating a node to each of the unknot, to each of the two handle, and then if they're linked, you put an edge between them. So all the linking numbers are assumed to be equal to plus minus 1 in this process. So this diagram is called Kirby diagram. This diagram here is called plumbing graph. It doesn't have to be a tree, as indicated here in this two examples. This is plumbing graph of linear AN chain. This is plumbing graph of the E8 manifold, which is famous Friedman's manifold that doesn't have a smooth structure. There could be possibly loops and various self-plumbings in those diagrams, but we won't talk about it. This actually, machinery of associating plumbing graphs to Kirby diagrams does not always work. So here is a cute example. You have 3 unknots which form a link called Borromean link, and the linking number between each pair of unknots is actually equal to 0. So if you are to associate a plumbing graph to this Kirby diagram, what you would have 3 nodes, 3 vertices, each carrying label 0, because I chose to label it by 0, and they wouldn't be connected by any edges because there is no linking. They are not linked, each individually. But this is very different from 3 unlinked circles which just sit separately in 3-dimensional space. So I want to point out that there are limitations to this plumbing graph presentation compared to Kirby diagrams. Nevertheless, it's enough for the purposes of this talk, and we're going to learn some interesting things just by focusing on this plumbing graphs, and I'll limit myself to the trees where there are no loops in the quiver diagram. Before we proceed, I want to point out the following. Any 4 manifold, it turns out, could be built by starting with, say, 1 handle and then successively building up a more complicated structure by attaching additional 2 handles. So you basically increase second Betti number in a sequence of steps, and there is a very simple exercise based on so-called Norman trick that shows that there are actually many ways to build same 4 manifold in this procedure by sequence of cobordisms. This Norman trick is a good exercise in Kirby calculus, which goes a little bit beyond the standard exercises in textbooks, but it has one important consequence for us. If 4 manifold can be built by a sequence of such steps, and we already know that cobordism corresponds to a domain wall between different 3-dimensional theories, it basically means that you can start with a very simple boundary condition, and then every time you want to make 4 manifold more complicated, you just put a domain wall which interpolates between different 3-dimensional theories, and by putting a sandwich of such domain walls, one for each cobordism, you basically build 4 manifold one step at a time, and then once you collapse the sandwich together, after all, in the infrared, it flows to a single boundary condition for the theory which is all the way on the right, then you end up with a corresponding 2-dimensional theory which describes the result of such building process. Now, for Vafa-Witten partition function, it has one more interesting implication. If you think about it, basically what I told you is that if you know basic cobordisms which describe how to attach one knot or one handle at a time, you're in business. So if only we had a couple of examples of Vafa-Witten partition functions or such theories in some special cases, we could probably take their difference and extract the corresponding cobordisms, and then we could construct more general form manifolds. Luckily, we have, due to work of Nakajima and Vafa and Witten, if this plumbing graph is Dinking diagram of AD type, then we know what the corresponding Vafa-Witten partition function is, or the corresponding theories. It's just the character of the corresponding group G, where geometry translates into group and number of 5 branes translates into the level. So what you learn thinking about it is that to each such basic cobordism, you should associate branching function of coset models if you're trying to decompose G characters in terms of H characters. So that's the second new result for Vafa-Witten partition function, and together with the first one and a couple of other tricks, we can actually build now Vafa-Witten partition function for any form manifold of this type. Okay, so the last thing I want to tell you is the following. We already mentioned that these plumbing graphs, which represent form manifolds, are kind of similar to quiver diagrams of 4-dimensional or other dimensional theories. So let's take this intuition a little bit more seriously, and let's play the following game. If you see a plumbing graph like this, oops, what happened here? So, if you see a plumbing graph like this, it may be a very complicated graph with loops and so on. To every vertex of the graph, you're going to associate gauge field in 3 dimensions. N equals 2 3-dimensional gauge multiplet. I call the corresponding superfield V, and usually we associate the label of the vertex to the rank of the corresponding field. So here it's not going to work because this can be positive or negative. So what we'll do to each vertex, we'll associate U1 Chern-Simons term at level A. So the label of the plumbing graph will become the Chern-Simons level of this U1 supermultiplet, and this is the only kinetic term that we're going to assign to this graph. Now, to a link which links to edges, as in this complicated graph, we're going to associate bilinear Chern-Simons term which couples these two together. This theory, even though it's a abelian gauge theory, its number of U1 factors is the same as the number of vertices, and it has a lot of information, basically all the information about the plumbing graph, is actually quite interesting. Even at the bosonic level, it was studied by a number of authors, and they found that there is an interesting classification of such theories, there are interesting transformations, and here we're talking about supersymmetric version, even though fermions actually decouple, so it's not that much different. So let's look at these theories a little more closely and follow our dictionary. So here is the first example of such quiver 3-dimensional N equals 2 quiver Chern-Simons theory. It has 2 vertices which are possibly attached to the rest of the plumbing graph, and let vector field for this superfield for this vertex to be V, superfield for this vertex to be V tilde. Then according to the rules, we should have Chern-Simons terms at level 1 for this guy, at level A plus minus 1 for this guy, and there is a couple between them because there is an edge connecting these fellows. Okay, so I'm just following the simple rules of building quiver Chern-Simons out of the plumbing graph. Well, this superfield which comes with this vertex plus minus 1 enters only to the 2 terms here, the link which gives rise to the bilinear term and the Chern-Simons level 1 or plus minus 1 for this guy itself. So let me integrate it out, because this is quadratic action, so I can try to integrate out the vector superfield V by solving its equations of motion. Well, its equations of motion tell me that V tilde, if I minimize this action, it's easy to see that V tilde is minus plus V, so substituting it back we get this, and coefficients were chosen in such a way that after the dust settles, you end up with the Chern-Simons term just A, V tilde sigma tilde. So we shifted this label A plus minus 1 to make it A, shifted it by 1. So if you read this, it basically says that diagrams associated to such quiver Chern-Simons theory of this form and this form should be equivalent. I just related them by integrating out a multiplet. And if you followed what I just said in the last 2 minutes, you learned about a Kirby move. So this is one of the examples of a Kirby move called blow up or blow down, where you add vertices or remove vertices according to some rule. Well, when I go through textbooks on Kirby calculus, I never remember what goes to +1, what goes to -1, and all these details. But hopefully, I'll tell you the derivation of these Kirby rules just from the physics of three-dimensional Quiver-Chern-Simons theories. So it's much better, in my view, to know the strategy or method how to derive the rules rather than memorizing the tables. And this is one illustration of one Kirby rule. There are a couple of more. Basically, all of them involve vertices which carry labels +-1 and 0. So let me illustrate just one more rule for you. So we discussed analog of this +-1 business. So let me pick one rule where you have vertices labeled by 0. So this one, for instance. In the dictionary between this Kirby diagrams or plumbing graphs and Quiver-Chern-Simons theories, we're supposed to associate vector superfield to each vertex and bilinear Chern-Simons to each link. So here, if you have framing coefficient 0, something special happens. Namely, this vector superfield V doesn't have its own Chern-Simons term, because A, the label here was coefficient of the Chern-Simons. So the only way in which vector superfield phi enters is via bilinear term corresponding to this link here. So therefore, it appears in the Lagrangian only in a linear way. This is now Lagrange multiplier. And therefore, integrating out this vector superfield V basically imposes the condition that V tilde is pure gauge. And if V tilde is pure gauge, then we're supposed to drop all of that Chern-Simons terms. And therefore, if you have something of this form, where V couples to V tilde, which in turn may couple to lots of other things, you're just supposed to disconnect everything, remove these two vertices, and the rest of the plumbing graph is supposed to be disconnected. So that's another rule, how you derive another Kirby move. Of course, you can verify that everything else I showed you on the previous slide can be derived in the same way. And again, I emphasize that, at least to me personally, it's much easier to remember Kirby moves in this way rather than memorizing what they are from the textbooks. So to summarize, there is a dictionary between 4 manifolds and 2-dimensional heterotic-like theories, which don't have to be non-anomalous. That's okay, because they may couple to 3-dimensional theories. In these moves, so-called Handel slides or Kirby moves correspond to various dualities of either 2-dimensional theories or 3-dimensional theories associated to the boundaries. We talked about domain walls corresponding to cobordisms between 3 manifolds. The fusion of domain walls corresponds to stacking these domain walls or manifolds together. Waffen-Witten partition function corresponds to superconformal index with various flavor parameters and so on and so forth. So I hope this has been interesting new correspondence between math and physics.
Thank you. Greg.
Do you actually prove some of those lines correspond to unitarity bounds in zero-tooth models, or is it a suggestion?
No, that's a suggestion. It actually holds water, but at this point I talked about topological 4 manifolds. All those bounds refer to smooth structures, and this is much more interesting part of the story, which I didn't talk at all about.
Do you have a room for the generalized Noether inequalities in terms of interpretation, in terms of unitarity bounds?
I hope so, but before we get there, there should be definitely room for Donaldson invariance and lots of interesting things found with smooth structures. Which
you mentioned basic classes on the slide, so that's why I asked.
Perhaps part of your continuation of your talk, does your 4 manifold have to have a smooth structure to get a 2-dimensional theory or not?
It seems that it doesn't, and actually, to me, that's a very interesting, puzzling question, because normally when we formulate something on a 4 manifold in terms of field theory, such as topological twist of Super-Yang-Mills, we use derivatives. So we write in terms of fields and so on. But for some reason, it seems that the story may even work on non-smooth manifolds. I think that's an excellent question again. So I relegate all the questions about smooth structures to future work, which I think is extremely exciting. And this question is very delicate because it depends, for instance, whether we talk about 4-manifold or 4-manifold with just one removed point. It makes a huge difference in terms of smooth structures. And there are tools to analyze this question. For example, the tensionless strings of 0-2 theory would be a great tool because they can wrap surfaces, embedded surfaces, for a manifold and tell us about chiral ring of 0-2 two-dimensional theories.
Okay, we probably have to stop here because we have a very tight schedule. So we thank the speaker again.